Today we're going to talk about the 4-gas detector, in particular the MSA Altair 4X, although most of what I'm going to say applies to any 4-gas detector out there. Some of the details will be different, the big picture is exactly the same. So, what gases does the 4-gas detector detect? What 4 gases? The 4 gases are LEL. On our current 4-gas, that's called combustible explosives. And it measures in what unit? It measures in percentage. The next thing it measures is oxygen. And again, it measures in percentage. The next thing it measures, carbon monoxide. And that's a different unit. That measures in parts per million. The final thing it measures is hydrogen sulfide. H2S, measuring in parts per million. Now those 4 gases, they're not some magic 4 gases. They're not random 4 gases. Those are the 4 gases that are required by law for entry into a confined space. And they're also pretty applicable to the rest of firefighting, especially these 3. We'll go in each one of them. We'll talk about the nuances and the weirdnesses of the sensors, the stuff you have to know, and then the maintenance of the machine one by one. First things first, the LEL sensor. This is arguably the most important sensor on the entire machine, because if you walk into a super poisonous environment, but you've got your SCBA on, you're probably going to be okay. But if it's a flammable environment and it catches on fire, if it flashes or explodes on you, you're probably dead or severely injured. So the LEL sensor is really important. It's a little bit different from the other sensors. I'm not going to get into the details of how it works. I'm not going to get into the details of the Wheatstone bridge, but at the heart of it is a little bead of platinum with a whole bunch of little holes in it. And this bead gets heated up. And when gas comes, even though there's not enough of it to actually burn, say we had 1% of gasoline vapor in the air, it would burn on the surface of this bead because the bead is catalytic. So let's just, it's not exactly right, but let's say there's a little bit of, quote, fire on this bead. That'll heat the bead up more, and it'll change the electrical resistance going through there. So the little microchip in the detector goes, oh, the resistance of the platinum bead has changed, therefore there must be something flammable in the air. Because it works like that, anything that's flammable in the air, anything that's got enough vapor to off-gas, will show up on this detector. So it is a gasoline detector. It's a natural gas detector. It's an acetone detector. It's a xylene detector. Anything that you can light a match to and will burn, like not wood, because that's not putting off enough vapors, but anything that produces enough vapors that would create a hazard for exploding, this thing should be able to detect. The caveat is, though, it only detects high levels of that gas. It doesn't detect low levels. It's not like the photoionization detector on the hazmat truck that can go down to the ppm. This is in the thousands or tens of thousands of ppm. So it's the LEL sensor, and it's in percentages. So what does it detect? Let's take a gas. Here's 0% gas. Here's 100% gas. Nothing but gas in this entire room. And let's take propane. Propane's got a flammable range about from 2% to 10%. What does flammable range mean? Flammable range is the distance between the LEL and the UEL. Up here, it's too rich to burn. Down here, it's too lean to burn, and in between, you get fire, you get explosion, you get other bad stuff. So the LEL sensor goes from 0 to 100%. So let's say that the top left-hand number here, where it says combustible explosives, is reading 50%. That's the reading. Where are you on this number line? Hint 1, you are not here. It's not the how much gas is there in this room sensor, it is the LEL sensor. It's how far am I between being completely safe and being in an environment where it could explode. So 50% in this case of propane is halfway between 0 and 2%. This is the LEL. So if we blow this up, this is 2% propane, this is 0% propane. 50% would put you halfway, which is 1% propane. just for some fun hazmat math, 1% is equal to 10,000 parts per million. So it's a lot of parts per million by the time this even gets a low reading here. How can you remember this? It's really easy. 100% is equal to how many million parts per million? It's equal to 1,000,000 parts per million. Then you knock off a couple of zeros, and you're left with 1% is equal to 10,000 parts per million. Let's take another gas. Let's look at another gas. Let's take a look at methane. So we got methane here. Flammable range from 5% to 15%. Let's say this thing is reading 10%. The number here is 10%. Where are you? Well, as I said before, you're not at 10% of methane in the room. You are 10% on the way to being screwed, with 5% being completely screwed. If you were walking around with a lighter, at 0% you'd be fine, 1% you'd be fine, 2, 3, 4% you'd be fine, and somewhere around 5%, kaboom. So if this reading is 10%, you're 10% on the way to being screwed. For the math nerds in the audience, what percentage methane would that be? That would be 0.5% methane. My next question, what parts per million is that? Well, if 1% is 10,000 parts per million, this is 5,000 parts per million. Just so you know, there are correction factors for the combustible gas sensor, the LEL sensor. Some gases, the sensor is more reactive to, some gases it's less reactive to, but the ranges of correction factors are much smaller than for the photoionization detector. So it's not something we worry about too much. It's a very large margin of safety. So let's talk about that margin of safety. WorkSafe used to be WCB, and WCB used to say that 20%, you could go into a flammable environment up to 20%, and then you had to back out. They've gotten rid of that. It's now 10%. So I'm in hall 1, I'm in the TV room. If there was a propane cylinder open in the kitchen, creating a flammable explosive environment in the kitchen, over here I might only be reading 5%, 10%, 15%. But if that blows up in the kitchen, if that gas cloud hits the pilot light and explodes, I'm still going to get in trouble here. I'm still going to get injured, hurt, or killed here. So that's why you have a margin of safety. Another example is, years ago, there was a warehouse. It had natural gas heaters. There was a natural gas line. That natural gas line got ruptured by a forklift, and it was just pissing out of here. We went in through the door at the bottom and got a reading of about 12%. So that's 12% on the way to the LEL. So I could have had a match here, I could have had a welding torch, I could have had flint and steel. It would have been okay. No amount of sparking here is going to explode that. But somewhere up here, there is a flammable zone. Natural gas is lighter than air. Therefore, somewhere up here is 100% of LEL. And if that 100% of LEL hits some kind of ignition source, that's going to explode up here. And me being down here going, I'm at 12%, I'm safe, does not actually apply, because that roof's going to come down on top of me. So there's a big margin of safety built in with the 10% of LEL. Now, of course, if we're going and we're going to put, a lid on a gas can that's out in the middle of a field with no ignition sources, and we hold our foregas right up to the mouth of the gas can, it's going to go over 10%. Probably going to go over 100%. Doesn't mean that we back out. In that isolated case, with no ignition sources, we can put the gas cap on. So it does have to be measured. This is definitely an issue, though, when you're entering into a space or when there are high amounts of gas everywhere, spilled fuel truck or something. Then you really got to start paying attention to this 10% back out quantity. 3 more things about the LEL detector. If you go into a really rich environment, or say there's an excavation here, they've ripped a natural gas line, and you can hear it pissing out, it's going straight up in the air, and I hold my 4-gas detector into that natural gas stream, it'll go reading 0, 1, 2, 3, 100%, then XXX. XXX means you've gone over range. It means it's maxed out and it's had it and it's basically going to ignore you from now on. It's not going to go back down as you back out. So what you got to do here is you got to back out, go into completely clean air, and restart your machine. It's the only way to reset when you go over range. That's what XXX means. Second important thing, because that catalytic bead kind of sort of burns whatever gas is in the air, in order to burn it, it needs oxygen. If there's not enough oxygen in the air, then you're not actually going to get reliable readings of this. You actually need 10% of oxygen in order to trust your 4 gas detectors. So you back out when the LEL is 10% and you need 10% oxygen. So if you're in an extremely oxygen deficient environment, in a barge or in some kind of weird lab or something, and you're at 5% oxygen, say, obviously that's an ideal H environment, we'll talk about that next, but you won't be picking up reliable readings for the LEL. Now, if all of a sudden if oxygen comes into that environment, you might have actually been in the perfect range for explosion, but would have never known it. So you do need 10% oxygen for this to work properly. The final thing we got to talk about, and it's really important, are sensor poisons. Sensor poisons are things that kill the sensor. The very worst one is silicone. If you think like a spray lube or you think Armor All, then you can really screw up your LEL sensor very quickly, just a few parts per million. Burnaby Fire had an issue years ago where the probies were cleaning the inside of the trucks with Armor All and it was killing all of their 4 gas detectors. Unfortunately, when it kills the 4 gas detector, in particular the LEL sensor, it's not like the LEL sensor goes, ah, I'm dead. The LEL sensor goes to show 0. So you could go into a flammable environment, a legitimately flammable environment, and have that thing read way too low or even 0. So silicone, super poisonous, lead, super poisonous, other things like acidic gases, chlorine, hydrochloric acid, hydrogen sulfide, also really bad for the LEL sensor. So the bottom line is, you got to watch out what kind of environment you're using it in, and you got to bump this on the way to a call, because you don't know what the last guy did with it. Maybe the last guy, decided to clean it using Armor All and killed it, and you won't know until you bump and calibrate it, which we'll talk about closer to the end of this presentation. The next 3 sensors, the remaining 3 sensors, are what's known as electrochemical sensors. So imagine a little pot. There actually is a little cell inside the detector for each of the 3 gases, and it's full of chemicals, right? So there's some weird chemical in here. Chemical. This is a set of chemicals that's designed to react with the target gas. So let's say it's the hydrogen sulfide detector. If hydrogen sulfide comes in here, comes in, H2S, it reacts with the chemicals and it produces an electrical current. So it's sitting there fairly happily, fairly stable, but when the chemical comes in and reacts with the chemicals that are in the electrochemical sensor, it produces a current. This means a couple of different things. It means that over time, these chemicals are going to break down. These chemicals will break down a lot faster if there's a whole lot of this gas here. So say we were at a hydrogen sulfide leak and we're in high levels of hydrogen sulfide for hours, then this sensor might only last an hour, might only last 30 minutes, as opposed to normally sitting on the truck where it's not reacting away, it could last a couple of years. So they're consumptive. They do get used up over time, and they produce a slight electrical current. Because the chemicals get used up over time, these sensors drift. They don't produce, if we had this sensor here, and we go into a hydrogen sulfide environment of 10 parts per million, we're going to get a certain voltage. I don't know what the voltage is. Let's say it's 10 millivolts. Now we put that sensor back on the truck and we come back to that same room a year later. Now we might only be getting 5 millivolts. So you've got to calibrate the sensor, you've got to calibrate the detector over time to make sure that you're getting the right reading, even though these sensors are getting old and will eventually need to be replaced. So electrochemical, the next 3 are all electrochemical sensors. Let's talk about the oxygen sensor. This is really important for a bunch of different reasons. We already mentioned that we need oxygen in order to get good readings off the LEL sensor, but low oxygen and high oxygen can kill us. What is the ideal H of oxygen? And what is the normal level of oxygen? The normal level of oxygen is 20.8% in air. The rest is all nitrogen. We start getting into trouble at greater than 23% and less than 19.5. Lower is easier to understand than higher. If you start dropping oxygen levels lower and lower, lower, you'll get sleepy, you'll go unconscious, and you'll die. But long before that happens, you'll lose judgment. So if we kept on dropping the oxygen in this room, then below 19.5, your judgment-making abilities will be impaired. So that's why 19.5 is considered ideal H by law. It's not that it'll kill you. You could live there for a very long time, but you'd have very poor judgment. And if that continues to change, or if the situation gets dangerous in any way, you might not have the judgment to get out. So less than 19.5, you got to be on a BA. Greater than 23%. This is confusing to some people because if we breathe oxygen, then oxygen is good, right? Well, oxygen is also an oxidizer. It's the original oxidizer, hence the name. So as we start going up 23, 24, 25, 30%, a fire will burn much more intensely. An explosion will be much stronger, and things that aren't supposed to burn will start burning. At a high enough oxygen concentration, you can take a match, hold it to your Nomex fire gear, and it'll burn just like paper. This is obviously a very bad thing. So you've got to keep an eye on high levels of oxygen and low levels of oxygen. Oxygen enrichment basically has got to be an open oxygen tank, or there's got to be some kind of chemical process that's producing high levels of oxygen. Low levels of oxygen, more common. What are some things that can cause low levels of oxygen? Well, rust is a pretty obvious one. The famous example of the New Westminster barge, where the guys died, that was rust consuming the oxygen but not consuming the nitrogen, so the relative concentration of oxygen was dropping. Another is combustion. Obviously at a fire, or if there's a ton of welding going on in an area, or if somebody's decided to heat their house with a barbecue, all of which has happened, then you're going to start getting lower levels of oxygen. Another one is fermentation or rotting. If we were at a place where there's a ton of rotting vegetation in a confined space, it's using up oxygen as it rots, it's going anaerobic. Or if we're at some kind of brewing facility, a beer brewing facility, it's using up a lot of oxygen as it's fermenting, as it's rotting. So fermentation is another problem. The final common one is displacement. So oxygen is 1/5 of air. The rest is basically nitrogen. So if we had a giant nitrogen tank in here and we opened it, as it fills the room, it's squeezing out the oxygen. It's not eating it up, it's not destroying it, it's just pushing it out, it's displacing it. And that can kill us, that can make us have bad judgment, that can make us go unconscious, that can kill us just as much as anything else. So displacement is another thing. And this brings us to a really important ability of the oxygen detector, and that's to detect other things that are going on in the atmosphere other than oxygen. Let's say this is the atmosphere, and let's say this is the component of oxygen. If we're displacing stuff in here with some other kind of inert gas, let's say we're using argon, each molecule of oxygen that we kick out, because this is only 1/5 of the whole room, we've got to kick out 4 molecules of nitrogen. Fire hall math, more or less, right? That means that if your oxygen sensor goes from 20.8 to 20.7, which is the smallest change it can register, it's a 0.1% of a change, it can be as much as 5,000 parts per million of something else. Now, earlier I said that 0.1% is equal to 1,000 parts per million. Actually, I didn't say that. I said 1% is equal to 10,000 parts per million. So how here is a change of 0.1% equal to 5,000 parts per million? It's because of this 1 to 5 relationship. So if you can't remember that math, just remember this. A tiny change in the oxygen reading, the smallest change possible, 20.8 to 20.7, means that there could be a significant displacement of the atmosphere. And when you get into hazmat, there are a lot of things that can really hurt you at 5,000 parts per million. That's a pretty big number, and there are things that are toxic at way lower levels than that. So if you go into a space and you notice the oxygen dropping, you got to back out and figure out what's going on. Okay, is there something else here? Is this oxygen sensor just getting old, or have there been large changes in humidity or temperature? Because that can also cause the oxygen sensor to swing. So if you go from here into VersaCold, into a freezer room, and shifts 40 degrees Celsius, 50 degrees Celsius, that oxygen sensor is going to do some funky things. It doesn't necessarily mean there's displacement, but it means it could be displacement. Time to figure out what's going on. A tiny change in the oxygen sensor can be a huge increase in something else. The next 2 sensors are pretty quick. Carbon monoxide. Carbon monoxide, invisible, tasteless, colorless, odorless, bad stuff, product of incomplete combustion. 1 carbon, 1 oxygen bound together, and if you breathe it in, it'll bind to the hemoglobin in your blood and asphyxiate you from the inside out. We go to lots of CO calls, and that's why it's very handy to have the CO sensor on the 4-gas detector. The time-weighted average, meaning you can be exposed to it for 8 hours a day, 5 days a week for carbon monoxide, is 25 parts per million. The short-term exposure limit is 100 parts per million, which means you can be exposed to it for 15 minutes at a time for 4 times a day. So you can take a fair number of ppm. As you start getting higher, you start getting dizzy, you start getting nauseous, you start feeling flu-like, and eventually you die. But it's not like, oh my God, there's 2 parts per million of carbon monoxide here. That's not a good thing. We've got to figure out why there's carbon monoxide in a house. But it's not like we're going to die right away. One thing that a lot of people don't know is that between roughly 12% and 75% concentration, percent, not parts per million, carbon monoxide is flammable. That's the LEL, that's the UEL. So you add some oxygen and an ignition source to this and kaboom. That's what a backdraft is. A backdraft is an explosion of carbon monoxide mixed in with an explosion of hydrogen cyanide, which is also flammable, and all the crazy organic chemicals, acrolein, glutaraldehyde, formaldehyde, benzene, all of those that are super poisonous and flammable. So that's also way beyond the range of our detector. Our detector is in this range here, the low ppm. By the time you get into the super crazy high ppm, maybe the LEL pick it up, or maybe the fact that there's big billowing clouds of black smoke coming out of the building will be another clue that the CO is high. Final thing to remember about carbon monoxide sensors is there are lots of cross sensitivities. This sensor picks up a lot of other gases and gives readings when it's exposed to other gases. We'll discuss that in a little bit. Now let's move on to hydrogen sulfide. H2S, hydrogen sulfide, is a sewer gas. It smells very, very sulfury, very pungent at low levels. When it's at low levels, you can smell it. As it gets to higher levels, it actually wipes out your sense of smell, and you can't smell it anymore. It's also poisonous, it's also flammable, it's also corrosive, so it's generally bad stuff. And there are much lower allowable limits of this than there are for carbon monoxide that we just covered. When I worked up on the Alaska slope for the oil and gas industry, we had to spend a half day on a hydrogen sulfide lecture and training before we were allowed to go anywhere near those oil wells, because there's so many oil wells up there that produce gas and oil and release hydrogen sulfide. Here in Delta, we're mostly going to find it in sewers, or maybe possibly in a fermentation type situation. It's not, maybe it's to do with the oil and gas industry. It's not that common. It's also used industrially, but if we do find it, it's really bad stuff. The time-weighted average, 1 parts per million. So basically, as soon as you can measure it, you're not supposed to be there. The short-term exposure limit is 5 parts per million. And remember, it is flammable at higher levels, it's corrosive at higher levels, and it's poisonous at low levels. So it's really not good stuff. A cross-sensitivity is when a sensor designed for one chemical, the target chemical, picks up another chemical and gives you a reading. It can be positive or negative. Now, The LEL sensor and the O2 sensor don't have many cross sensitivities per se, like pure cross sensitivities. There are things that can cause both of those sensors to give bad readings. We've covered them. What are they again? They include sensor poisons, especially for the LEL, right? Silicone, lead, acidic gases. They include temperature or humidity swings for the O2, and they include low O2 for the LEL sensors. So low O2. These are for the LEL sensors, this for the O2 sensor. So those aren't great, but they're not cross sensitivities per se. A cross sensitivity is when the sensor gives a reading that it shouldn't be giving for the gas. Now we've added to the black 4-gas accessory box on the trucks a sheet of the known cross sensitivities for both the carbon monoxide sensor and the hydrogen sulfide sensor. I say known because these are the only ones they've tested. I'm sure there are many, many more. So if you end up with some weird chemical, it might have a reaction with one or both of those sensors. We don't know every possible cross sensitivity. But here are some common ones, and it shows you if it's positive or negative. So years ago, there was a warehouse. It was a warehouse full of cleaning supplies and cleaning equipment, and it was getting readings of carbon monoxide. Crew went down. There was no source of combustion. It was electrical heating, not gas heating. There had not been a fire of any type. There had been no trucks parked up, backed up to the warehouse, pumping it full of carbon monoxide. No sources of carbon monoxide. But they were getting readings, the crew as well as the alarms in the facility. So they found the highest readings near some floor polishers that were being charged, big lead acid batteries. Lead acid batteries release hydrogen when they're being charged. So they were getting readings on the CO detector, which makes sense. When you take a look at your cross sensitivities for the CO detector, it'll show you that hydrogen, if you had 100 parts per million of hydrogen, you'd get a reading of 48 parts per million of carbon monoxide. There's no carbon monoxide, it's just giving you that reading. So the good news is, if you have a carbon monoxide sensor, you also have a hydrogen sensor. But you need to know this, so you need to know that this exists, and you need to know how to use it. Another example, say we were going into Sun God. There was a report of some kind of situation, we're wearing our SCBA, so we can't smell anything, and our hydrogen sulfide detector starts giving us negative readings. So now a negative reading is a pretty good example or a pretty good indication that you've got a cross sensitivity going on, because you're not supposed to get negative levels of hydrogen sulfide. So you consult your handy dandy cross sensitivity sheet, and I've conveniently picked one that's on here. Chlorine has got a negative cross sensitivity. If 100 parts per million of chlorine, you get negative 14 parts per million of hydrogen sulfide. Again, there's no hydrogen sulfide there, it's giving you that reading. So now you combine the reading on the detector with your knowledge of the facility. Yeah, there's chlorine here. Yeah, there's ammonia here. One of those has got a negative cross sensitivity, the other's got a positive cross sensitivity. So which one of those things is leaking? It would be chlorine. So now you have an indication that it could be chlorine, you back out and you figure out a plan to deal with a potential chlorine leak. So the presence of cross sensitivities is both a blessing and a curse. It can work against you if you're not aware of them, and it can work for you if you know that these exist and you know roughly what the numbers are. I wouldn't say it's as good as having a chlorine detector or having a hydrogen detector, but it's way better than not having any kind of detector at all. Next thing is going to be quick. It's the pump probe. A lot of people don't know that we have this. A lot of people don't know that the batteries need to be changed on this. And, I found a lot of dead ones here. So hopefully this video will change that. This is an electrically powered pump. You can hear it pumping away there maybe. With a probe, there's a little tiny filter right here to stop a few drops of water from coming through, or liquid. If you're going up to test something, don't jam this into the liquid. It'll suck a whole bunch of liquid up here, through the pump, and into the detector, and probably break both the pump and the detector. This is only a fail-safe for like a drop of water, a drop of liquid, then you got to replace the filter. So this screws in here, goes in, very simple to use. So you hear that beeping? That means we've blocked the airflow. We push the button again, to reset it. If we block this long enough, the pump will labor and it'll eventually go into alarm again. Basically, you take this, you take the adapter for the bumping and calibration, you snap the black claw onto your 4-gas there, you attach this onto the claw, and now you have the gas being brought to this detector in a powered way rather than a passive diffusion way. So the sensors will work faster. You do have to account for the time it takes for the gas to traverse the wand, the probe, the pump, and this tubing, but in general it's better. So you can also use this if you had to measure really high, you can get a reading. If you had to measure really low, you can get a reading. Just remember, you got to wait there a couple of seconds, 5, 10, 15 seconds, to give these sensors time to work and time to catch up to what's being read. Remember, you should be checking high, middle, and low, especially high and low. If you're dealing with a real heavy gas, a complex organic, you might only get a reading in the bottom couple of inches above the floor. That's where it's flammable. It might not be giving you a reading up here. So that's where the wand comes in handy. Or if you've been in a place where there was a methane leak, maybe, and it's very calm, maybe that methane has gone up into the ducting. So you could poke this up and you wouldn't have to like climb up as much. So the pump probe, turn on, turn off by pushing the green button. And to change the batteries, we have two styles. Number one, you can unscrew the bottom here. A couple of AA batteries go in there, close it up, it works again. There's another style of pump probe floating around that needs to be plugged into the wall. Please make sure that they're charged. It's something that we should be doing on Sunday truck check day. Making sure that these work, making sure they turn on, turn off, making sure that the air flows, and making sure that if the batteries need changing, they either get changed or charged. Two more things, then we're done. So the next thing we got to talk about is peaks. Let's say that you and I go into a place, this thing goes into alarm, we panic, we run out, the IC asks us, what was the highest reading you got? Maybe we only remember one number. Maybe we remember the wrong number. He can, if this has been done properly, go into the peaks, or we can go into the peaks, and that tells us the highest reading that this thing has been exposed to since the last time we cleared the peaks. Another example might be if we had a reading, we need a reading down a hole, we could tie this to a string, lower it down, and then slowly raise it up, and we go into the peaks, and then it would tell us the highest reading that it found in that air column, so long as we've cleared the peaks. So clearing the peaks and seeing what the peaks are related, basically you're going to push the down button twice. If you push the down button twice, this symbol here should appear at the top of the screen, giving you the highest reading that it's been exposed to. Then you click the up button once, and that clears the peaks. So down twice to see them, or to scroll through the options, up once to clear them. It's also in the instruction manual. So that's really important, and we should ideally be clearing the peaks before we go into an environment. It should be after the bumping, after the calibration, we clear the peaks every time, just to make sure that the last thing this thing remembers is 0% LEL, 0% H2S, 0 ppm H2S, and 20.8 oxygen. Last thing, very, very important. Bumping versus zeroing versus calibration. I'm not going to take you through the specific steps on how to do that. There are sheets in the black box of 4-gas accessories that take you through it. I have to consult them as well. I can never remember to push left 3 times and push up once, then wait 10 seconds. I can't do it. That's why there's a sheet. But you can accomplish each one of these things. So let's start with zeroing. Zeroing, you're telling the machine that you are in clean air machine. You should be whatever numbers you're getting, reset them so that whatever you're reading here is 20.8% oxygen, 0 hydrogen sulfide, 0 CO, and 0 LEL. So clearly you need to do this in a clean environment. You can't do it standing right beside the truck exhaust, because you're going to totally give it a false baseline. You normally do this when the thing's starting up. It asks you, do you want a fresh air setup? Fresh air setup is another name for zeroing. Of course, every manufacturer uses a different term, but in all these detectors there's something called zeroing, telling it you are now at baseline. This is clean air. Bumping. Bumping is giving this detector a shot of this gas. We carry this gas on the trucks. This gas is a known quantity. It's got 58% of a flammable, 58% of LEL of a flammable gas. It has 60 parts per million of carbon monoxide. It has 15% of oxygen. It has 20 parts per million of hydrogen sulfide. Clearly, if you were to breathe an entire room of this, it'd be very bad stuff. But it's good to check that all these readings are in fact working. So the simplest way to bump this, I don't actually recommend this, but if your mind goes blank, you take this, you screw on the regulator, you make sure there's some pressure in here on the regulator, and you flow this gas over this detector using the claw that we used earlier, using this claw. If you get readings plus or minus 10% to the readings that are on here, you're good to go. This thing kind of sort of works. The disadvantage with doing things that way is that you've now given it higher peaks, right? It's going to remember 58% LEL. If we then walk into an apartment and we get 12% of LEL, that's bad. An apartment shouldn't be at 12% of LEL. And we come out and we check peaks, we're still going to get the 58% that's here. So you got to clear peaks. There's also an entire procedure for bumping on the sheets, in the case. The trick there is as soon as it's done bumping, you got to detach this. Otherwise, it's done bumping, it goes into sensing mode and it still catches some of the residual gas coming through and it'll give you false peaks. So it's always a good idea to clear the peaks after bumping and after calibrating, just in case it gets a whiff of the old gas. So as an officer, if I'm going to a gas leak, smell of gas, methane leak, propane leak, I want to hear the process of the bumping going on in the back. Because, as I said, if this thing's been exposed to sensor poisons yesterday, or the day before, or the month before, and nobody's bumped it since then, I won't know until it doesn't read this. So bumping on the way to a call is required by law, and it's also a very, very practical thing to do because you want to make sure that this thing works. It's flying by instruments. You can't see LEL. You can't see carbon monoxide. You've got to trust your instruments. How do you trust your instruments? Well, you bump and you bump them first, you zero them, and then the final thing is you calibrate them. So we're supposed to bump every week or on the way to a call before entry, essentially. And we're supposed to calibrate once a month, the first Sunday of every month, or if there's a problem. If we're getting weird readings on here, I am actually getting weird readings on here because this is a new one that we just put into service. If we're getting weird readings on here, we got to zero it, then we got to calibrate it. Calibration resets this to read this exactly. Remember I said the electrochemical sensors drift over time? They produce less electricity for a given amount of gas. So by telling it, no, 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 detector, you are in 58% of LEL. You are in 15% of oxygen. Adjust whatever math voodoo is in here so that whatever reading you're getting translates out to 15%. It then allows it to reset itself even as the sensors get older. So zeroing, super important. Bumping, mega important. And calibration, very, very important for the long time life of the thing. Once again, we should be bumping once a week, typically Sundays, or before entry, and we should be calibrating once a month, or if there's some kind of problem. Okay, so there's a whole bunch of resources out there now. There's information about cross sensitivities, there's information about sensor poisons. Talk to your hazmat nerds, but I hope that's given you a good grounding in the 4-gas detector. Even if we go to a different 4-gas detector, they still all have the same limitations. The exact cross sensitivities might not be exactly the same, but they're going to be more or less the same. The numbers might be a bit different, but it's still going to have the same limitations, barring some brand new technology. All right? Thanks so much.